Introduction to Functions. So let's start our exploration of functions. This slide asks the fundamental question, what is a function? Now, in mathematics, a function isn't just any relationship. It's a special kind of relationship between two sets. You've already learned about sets, collections of distinct objects. A function builds on that idea. Specifically, a function is a rule. And this rule does something very specific. It takes each element from one set, we call this the domain, and assigns to it exactly one element from another set, which we call the codomain. Let me say that again because it's crucial. For every input, there's only one possible output. Think of it like a machine. Imagine you have a machine and you put something into it, that's your input, coming from the domain. The machine then processes that input and gives you something out, that's your output, which belongs to the codomain. But this machine is special. It always gives you just one thing out for each thing you put in. It can't give you multiple outputs for the same input, and it can't just decide not to give you anything at all. We'll be looking at examples of these machines, these functions in the coming slides, and we'll see how to define them and how to work with them. But this basic idea, a rule assigning one output to each input, is the core of what a function is. We'll build on this concept in the next few slides by breaking down the components of a function, like the domain, codomain, and the rule itself. Components of functions. So on the previous slide, we introduced the idea of a function, a rule that links inputs to outputs. Now, let's break down the different parts that make up a function. First, let's talk about sets. You've likely encountered these before. A set is simply a collection of distinct objects. Think of it like a list, but the order doesn't matter, and we don't repeat any items. For example, I've written here, A equals the set containing 1, 2, and 3. That means our set A includes the numbers 1, 2, and 3. Now, let's move on to the domain. The domain is the set of all possible inputs to our function. It's everything we're allowed to start with. Imagine you're building something. The domain is all the materials you have available to begin with. Next, we have the codomain. The codomain is the set of all possible outputs our function could produce. It's where the outputs come from. It's important to note that the codomain includes all potential outputs, even those the function might not actually produce for every input. We'll see that distinction later. Finally, we have the rule. This is really what the function is. The rule is what tells us how to take an input from the domain and get a specific output from the codomain. It's the instruction manual for our function machine. And here's the most crucial part. This rule must be consistent. For every input in the domain, there must be exactly one output in the codomain. No exceptions. If an input could lead to multiple outputs or no output at all, then it's not a function. We'll really drive this point home with some examples on the next slides, so keep that exactly one rule firmly in mind. A simple example. So let's move on to a concrete example to really solidify what we've discussed about functions, domains, and codomains. First, we're going to consider two sets. The first set, which we'll call A, contains the elements B and C. So, A is equal to the set containing B and C. We'll use this set A as our domain, remember. The domain is the set of all possible inputs to our function. Next, we have another set, B, which contains the numbers 1, 2, and 3. So, B is equal to the set containing 1, 2, and 3. This set B will be our codomain. That's the set of all possible outputs our function could produce. Now, let's define a function. We'll call this function f, and it will map elements from set A to set B. We're going to define this function by telling you what each element in A gets mapped to in B. So f of A is equal to 1. This means that when we input A into our function, the output is 1. Similarly, f of B is equal to 2, meaning B gets mapped to 2. And finally, f of C is equal to 3, so C gets mapped to 3. What this function f does is take each element from set A and assigns it a unique element from set B. It's crucial to notice here that each element in A, B, and C has exactly one corresponding element in B. A goes to 1, B goes to 2, and C goes to 3. There's no ambiguity, and no element in A is left out. This is a perfect example of a function because it adheres to the core principle. Every input has exactly one output. We'll build on this in the next slides, looking at more examples and also at what happens when something doesn't qualify as a function. Another example with numbers. Let's move on to another example, this time working with numbers. As you recall from the previous slides, a function takes an input and gives us a unique output. Here, we're defining two sets. The first set, which we'll call x, contains the numbers 1, 2, 3, and 4. We represent this set as x equals the set containing 1, 2, 3, and 4. This set x will serve as our domain, that is, the set of all possible inputs to our function. The second set, which we'll call y, contains the numbers 2, 4, 6, and 8. So y equals the set containing 2, 4, 6, and 8. This set y is our codomain, the set from which all possible outputs of our function will come. Now let's define a function, and we'll call it g. This function, g, will take elements from set x and map them to elements in set y. Let's define it as follows. G of 1 equals 2. This means when we input 1 into the function g, the output is 2. G of 2 equals 4, so inputting 2 gives us 4 as the output. G of 3 equals 6, inputting 3 gives us 6. And finally, g of 4 equals 8, inputting 4 gives us 8. Notice something? The function g simply doubles each number in the domain to produce the output. So, it's a pretty straightforward rule. This example reinforces the idea that a function is just a rule that assigns each input to exactly one output, and we've clearly demonstrated that here. Keep this in mind as we move forward, because we'll soon be looking at how to identify whether something isn't a function, and this example will be a good one to compare it to. Notation. Here we see f, a right arrow b. Now let's break that down. The f simply represents the name of our function. It could be any letter, really, but f is very common. So this entire expression is read as f maps from A to B, or more formally, f is a function from A to B. So now that we've looked at a couple of examples of functions and what makes them work, let's talk about how we write them down mathematically. This slide introduces the standard notation for functions. A represents the domain of the function, remember, that's the set of all possible inputs. And B represents the codomain, the set containing all possible outputs. So this notation is just a concise way of saying, we have a function named f that takes inputs from set A and produces outputs that are elements of set B. This notation will become really useful as we start working with more complex functions, and it's important to get comfortable with it now. We'll be using it throughout our study of functions, and it's the standard way mathematicians communicate about functions. In the next slide, we'll really solidify what makes something a function, and what doesn't, so keep this notation in mind as we move forward. What makes it a function? So let's solidify our understanding of what defines a function. As we've discussed, a function is a special kind of relationship, and there's one crucial rule we need to keep in mind. The key to a function is that each input in the domain, remember, that's the set of things we start with, must have exactly one output in the codomain, which is the set of possible outputs. Think of it like this. If you put the same thing into a function machine, it always has to give you the same thing out. Now, what happens if that rule is broken? If an input has multiple outputs, or even no output at all, then it's simply not a function. It doesn't meet the criteria. Let's look at an example to make this really clear. We'll use the sets we worked with earlier. Set A, which contains the elements of B and C, and set B, which contains the numbers 1, 2, and 3. Now let's try to define a rule, and this is where it will fail like this. We say that f of A equals 1, f of B equals 1, and f of C equals 2. Notice what's happening here. The input A and the input B both lead to the same output, which is 1. This violates our exactly one output rule. Because two different inputs, A and B, are both mapped to the same output, this relationship is not a function. Remember, a function demands a unique output for every single input. This is the fundamental principle that separates a function from just any old relationship between sets. We'll build on this understanding in the next few slides, so it's important to really grasp this concept. Key takeaways. Let's recap what we've learned about functions with these key takeaways. First, remember that a function is essentially a rule. This rule takes each element from a set, which we call the domain, and assigns it to exactly one element from another set, the codomain. Think back to the examples we've worked through. Whether it was letters mapping to numbers or numbers being doubled, there was always a clear, single output for each input. Next, we have a special notation to represent functions. We write it as f:(a right arrow b. The colon signifies maps from, and the right arrow indicates to. So, this simply means f is a function that takes elements from set A and maps them to set B. It's a concise way of saying everything we've discussed about the relationship between the domain and codomain. Finally, and this is crucial, for something to qualify as a function, every single input in the domain must have exactly one output in the codomain. No more, no less. If even one input leads to multiple outputs or no output at all, then it doesn't meet the definition of a function. We saw an example of this on the previous slide, where we demonstrated a relationship that wasn't a function because two inputs shared the same output. Keep these 3 points in mind, as they form the foundation for everything we'll be doing with functions. In the next section, we'll look at some common mistakes students make when working with functions, so we can avoid those pitfalls. Common mistakes. A common mistake is to think that any relationship between two sets automatically qualifies as a function. Now, we've spent the last few slides building up what a function is, a specific rule that takes an input and gives you a single, defined output. Just because we have two sets and some connection between them doesn't mean it's a function. It has to follow that exactly one rule we've emphasized. Remember, the exactly one rule is crucial. For every input you put into the function, there absolutely must be one and only one output. If you violate that rule, you don't have a function. Another area where students often stumble is confusing the domain and the codomain. Let's quickly recap. The domain is the set of all possible inputs to our function, everything we're allowed to start with. The codomain, on the other hand, is the set of all possible outputs the function could produce. It's the pool of values where the outputs come from. It's really important to carefully identify which set is which. Think of it like this. You're feeding things from the domain into a machine, the function, and it spits out results into the codomain. Getting those two sets mixed up can lead to errors when you start working with more complex functions later on. Let's move on to this final slide, where we discuss some common pitfalls students encounter when first learning about functions. So, keep these common mistakes in mind as you practice. If you can avoid these, you'll be well on your way to mastering the concept of functions.